Okay, worksheet 3 covers the remainder of solving first order ODEs. Talks about 3 different methods of solving ODEs, including exact ODEs, and those that you can solve by substitutions, including homogeneous ODEs and Bernoulli ODEs. And it also discusses the use of Euler's method in order to come up with a numerical solution to a differential equation. So let's get started with what an exact differential equation is. An exact differential equation is one in the form of m dx plus n dy is equal to 0, where the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And the methods on solving an exact ODE are given. This is the same as on the worksheet. And we're going to go ahead and start solving problems. So let me go to the next screen. Okay, so for these first couple of problems, it says to determine if the equation is exact, and if it is, then solve the equation. So I want to write this equation in the form m dx plus n dy is equal to 0. To write this equation in that form, I'm going to start by multiplying by dx. And when I multiply by dx, my equation becomes y over x squared dy plus e to the 2x plus y squared dx is equal to 0 times dx, which is still 0. So notice that here is my function m dx. Here's my function n dy is equal to 0. That's the form that I want it in. And this equation is exact if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And so let's see. Here my m is this exponential function. And if I take the partial derivative of m with respect to y, then I'm taking the derivative of this exponential function with respect to y. This 2x would be considered a constant. And because we have an exponential, we want to take the derivative of the exponent. The derivative of that constant is 0. Derivative of y squared would be 2y. So I get 2y times e to the, and then my exponent becomes 2x plus y squared. And notice that the derivative of n with respect to x it would be the derivative of y over x squared. Y over x squared is the same as y x to the negative second. I could bring that negative 2 down. I'm taking the derivative with respect to x. And I would get y x to the negative third. Not the same. So it appears that this isn't exact. However, many ODEs may be exact if you just rewrite them in a different form. So let me work this. So watch, if I take this equation and separate the variables by multiplying by x squared and by multiplying by e to the negative y squared, then my equation becomes y e to the negative y squared dy plus multiplying by e to the negative y squared will cancel out the e to the y squared that I have here. That x squared comes in front. I get x squared e to the 2x is equal to 0. Oops, I forgot my dx. So now my m is x squared e to the 2x. And my n is y e to the negative y squared. And when I take my partial derivative of m with respect to y, because this function doesn't contain any y variables, this would be considered a constant. I would get 0. And when I take the partial derivative of n with respect to x, again here, because my n doesn't contain any x terms, I would get 0. So now my equation is exact. So notice what we did here was we did separation of variables to make this separable. And if you can separate the variables, then when you do your partial derivatives, you're always going to get zeros, and therefore every separable equation can also be classified as exact. Okay, so let's see if we can solve this. In order to solve this for our first step, what we want is we want to create a function of x and y that's equal to the integral of either m dx or n dy. Most of the time we're going to start with m, although it's really up to you which side to start with. So we're going to start here. X squared e to the 2x dx. When you integrate this, you need to do integration by parts. And so off to the side, I'm going to let u equal x squared, and then du is 2x dx. dv is e to the 2x dx, and v is going to be e to the 2x divided by 2. So when I do this calculation, I'm going to get f xy is integrate by parts. You get uv minus v du. So I get u x squared v e to the 2x over 2 minus v du e to the 2x over 2 times 2x dx. These 2's will cancel. And I still have x e to the 2x. So I'm going to do integration by parts again. And I'm just going to switch out this u and that du. So now this time my u is going to be x for this x. And my du is going to be dx. But otherwise my dv and my v stay the same. So that I get my first term x squared e to the 2x over 2 minus, and then for this integral, again I have uv minus v du. U is x, v is e to the 2x over 2. That's going to give me x e to the 2x over 2 minus v du, which will give me e to the 2x over 2 dx. And when you do this integration, integrating e to the 2x, you're going to get e to the 2x over 2. That's going to bring another 2 down. So that ultimately I get x squared e to the 2x over 2. I'll distribute through by the negative here to get minus x e to the 2x over 2. This minus and this negative will cancel out to give me a plus. And then when I integrate this, I'm going to get e to the 2x and bring another 2 down to give me over 4, plus my constant of integration. Now here, because I have a function, f is a function of both x and y, and I'm integrating with respect to x, my constant is a constant in terms of x, which means that my constant could be a function of y. Okay, so here's my f of xy is this function. Now if I take the derivative of that function with respect to y, then I should get n. This part right here is my derivative with respect to y. Okay, when I take the derivative with respect to y, any terms that don't contain y's will drop out. So this term, x squared e to the 2x over 2, becomes 0. My second term becomes 0. My third term becomes 0. And the derivative of g of y with respect to y is g prime of y. And again, that should be equal to this n. That should be equal to y e to the negative y squared. Okay, next we want to solve for g. And to solve for g, we want to undo that derivative. And to undo this derivative, we want to integrate with respect to y. Okay, so to get g of y, we want to do the integral of y e to the negative y squared with respect to y. And here we're going to do a substitution. If I let u equal negative y squared, then du is going to be negative 2y dy Okay, so if I want negative 2y, I'm going to put a negative 2 here. So I have my negative 2y dy. But to put that negative 2 in, I have to balance it out with a negative 1/2 in front. So I'll get negative 1/2 e to the u du, which is negative 1/2 e to the u, and now my constant is just a constant, plus your constant of integration, which gives you negative 1/2 e to the u is negative y squared, e to the negative y squared plus c. So if I put this value for g of u back into my function here, I'll get my solution. My solution to the ODE is f of xy which is equal to x squared e to the 2x over 2 minus x e to the 2x over 2 plus e to the 2x over 4 plus g of y, which is minus 1/2 e to the negative y squared plus c is equal to 0. Whoa, sorry. I have a hard time drawing straight lines on this tablet. Anyway, this is the solution. Okay, on this second equation, notice that this one is not separable. There's no way to get this y out of this function. To determine if it's exact, I'm going to want to bring this dy term over to the left side so that I get x squared plus 2y over x dx minus 3 minus natural log x squared dy equals 0. So in this case, my m is x squared plus 2y over x, and my n is negative 3 minus natural log of x squared. To determine if this is exact, we're going to look for the partial derivative of m with respect to y, and we're going to look for the partial derivative of n with respect to x, and determine if they're equal. So my derivative of m with respect to y, this x squared term will drop out, and this second term, that 2 over x would be my coefficient, and I get 2 over x times the derivative of y, which is 1. On my partial derivative of n with respect to x, this negative 3 is a constant. The derivative of a constant is 0. This negative times a negative gives you a positive, and the derivative of natural log of x squared, would be 1 over x squared times the derivative of the argument times the derivative of x squared, which is 2x. Here you can cancel out an x to show that you get 2 over x in both cases. So this is exact. Okay, when I determine my solution is going to be f of xy is equal to 0. And I can start by integrating this function with respect to x, or integrating this function with respect to y. Because I don't have any y terms here, let me start. This will probably be the easier method. I'm going to integrate, let me bring that natural log first, because this minus and negative will make that a positive. Natural log of x squared minus 3, integrate with respect to y. And both of these are constants, so when you integrate with respect to y, you're just putting a y on. I'll just consider this as one constant. Natural log x squared minus 3 times y plus my function, and this time my my constant is going to be possibly a function of x. Okay, and then to find the partial derivative of f with respect to x, then should be equal to m. And partial derivative of f with respect to x, here you want to take your derivative, and when I take the derivative of this inside the parenthesis, I'm going to get derivative of natural log of x squared, we did up here, gives you 2x over x squared, which reduces to give you 2 over x, minus the derivative of 3 with respect to x is 0. This gets multiplied by y, plus the derivative of g, plus g of x. And that should be equal to m, which is x squared plus 2y over x. Now, here, any constant has to be a function of x. So any terms that don't contain x should cancel out. And notice that the y term does cancel on both sides. This 2 over x times y is the same as 2y over x. Those would cancel from both sides of the equation to give you g prime of x, this derivative of x, sorry, it should be a g prime of x, is equal to x squared. And to solve for g, you want to integrate with respect to x. When you integrate with respect to x, we'll increase the exponent by 1, divide by the new exponent, and then add our constant on. That's our g of x. And so our solution to the equation is going to be f of xy is equal to, here we have the natural log of x squared minus 3 times y plus g of x, which is x to the third, over 3 plus c is equal to 0. Whoa. And there's our solution. Now, if you want to rewrite the solution in a different form, you may want to solve for y. And to solve for y, you would bring these x terms over to the other side. That'll give you a negative x to the third over 3 plus minus c on the right side. And then divide by this coefficient of y. I think before... Yeah, let me just do that. So I'm going to get 3 natural log x squared minus 3, should be in brackets. That's multiplied by that 3. And if I write this c as 3 over 3, then I could combine these together so that I get minus 3c up here also. This may be a better answer because you've got it solved for y. Okay, and on number 3, if I multiply both sides of this equation by dx, that's going to leave me with 6x plus 1 y squared dy plus 3x squared plus 2y cubed dx is equal to 0. And this is my n. This is my m. When I do the partial derivative of m with respect to with respect to y, this x term drops out, and here I get 6y squared. And the partial derivative of n with respect to x gives me a 6y squared. So my partial derivatives are equal. It says that this is exact. And so let's see, which one would be easiest to integrate? 6x plus 1y squared dy or 3x squared plus 2y to the third dx? I think I'll start with my dx. We're going to let f, which is a function of x and y, equal the integral of 3x squared plus 2y cubed dx, which when I integrate with respect to x, I'm going to increase my exponent to 3 and divide by the new exponent, 3. That'll cause these 3's to cancel. It'll give me an x to the third. Plus, on the second term, it's going to put an x in there. 2xy to the third. Plus, because I'm integrating with respect to x, plus some function of y. Okay, so now I do my first partial derivative of f with respect to y. Take the derivative of this function with respect to y, and that first term drops out. On the second term, bring the 3 down so that we have 6xy squared. And on this third term, I'm going to get g prime of y. And this should be equal to n. When I distribute through by the y, I get 6xy squared plus y squared. And notice that these 6xy squareds cancel each other out to leave us with g prime y squared, or g prime of y, is equal to y squared. To undo the derivative, we want to integrate. That'll give us g of y equals the integral of y squared with respect to y. And here when you integrate, you want to increase the exponent by 1, divide by the new exponent, and then plus c. So our solution is f. We get x to the third plus 2x y to the third plus g, where g is y to the third over 3 plus c is equal to 0. Now, this is the answer, and if you want to leave the answer in that form, you may. If you want to solve this for x, you can, because we do have a y that can be factored out. So I'm going to factor out this y to the third to leave me with 2x plus 1/3. And I'm going to bring the other terms over to the right side. They'll become negative. Equals negative x to the third minus c. And then if I divide by 2x plus 1/3, bring that up here. It's going to give me y to the third equals negative x to the third minus c over 2x plus 1/3. And you'd want to get rid of that complex fraction. You can get rid of the complex fraction by multiplying by 3/3. And I think I'll leave this as y to the third, rather than taking the cube root of both sides. Multiplying by 3/3, we get negative 3x to the third minus 3c all over 6x plus 1. And there's our answer.